Okay, class, good morning. So again, this is another topic in the processes of ideal gases. So we have now here uh, on the fourth process. So this is isentropic process. Okay, so last time, so I already discussed to you the third process, which is the constant volume process. Okay, so let us now proceed to the discussion of this topic. Okay, so isentropic process or a reversible adiabatic process. So when we say adiabatic, so there is no heat transferred occur during the process. Heat gain or heat release, okay, is equal to zero. Okay, so let us now consider the illustration on the slide. Okay, so the first illustration is the PB diagram and the second one is the temperature entropy diagram. Okay, so knowing that the equation for isentropic process is PB raised to K is equals to constant, or the process again is S is equals to C, or entropy is constant. And Q, of course, since the process is adiabatic, Q is equals to 0. Anyway, so we will proceed to that one by one. Okay? So let us now go to the PBT relationship of this process. Again, so for ideal gas equation, PB is equals to MRT. Okay? So, getting now the from the equation, okay? So, PB raised to K is equals to constant, or P1 B1 uh, raised to K is equals to P2 B2 raised to K. Okay? So, substituting values now, and then uh, getting the temperature or the ratio of temperature in terms of the pressure. So that is equals to T sub 2 over T sub 1, P sub 2 over P sub 1 raised to K minus 1. Or simply in terms of the volume, that is B sub 1 over B sub 2 raised to K minus 1. Okay? So, let us now derive that equation or that previous equation. So, from the combined ideal gas equation, P sub 1, B sub 1 over T sub 1 is equals to P sub 2, B sub 2 over T sub 2. And the ratio of the pressure is P sub 2 over P sub 1 is equals to P sub 2 over P sub 1, T sub 1, T sub 2 raised to K. Okay? So, and then, getting now the ratio of the final temperature and the initial temperature, that is equals to P sub 2 over P sub 1 raised to K minus 1 over K. So, this is the first example in the, or the first equation in the PBT relation. Okay, so for the ratio of the temperature, that is P sub 2 over P sub 1 uh, raised to K minus 1 over K equals to B sub 1 over B sub 2 raised to K minus 1. Okay? So, for the non-flow process, okay, so we know already what is the basic definition or the basic equation of the work non-flow. Okay? So, that is always equals to the integral of the pressure multiplied by differential volume. Okay? So, from the equation again, PB raised to K is equals to constant, or P1 B1 raised to K is equals to P sub 2 B sub 2 raised to K. Okay, so getting now the pressure. So that is equals to C over B raised to K. Or uh, bringing now the numerator into the denominator. So that is P is equals to C raised to negative K. Since we put this denominator at the numerator. Okay? So that is negative K. So another, the work non-flow now is equals to the substituting values. So work non-flow is equals to the integral of C B raised to negative K multiplied by dB. Okay, so putting now the constant outside the integral sign. So that is negative b, or b rather, raised to negative k dB. Okay? So, and then, integrating now the this term. So that is now b raised to negative k plus 1. So we always add 1 to the n, and then over negative k plus 1. And then applying the limit from b sub 1 to b sub 2. So that is now equal to workman flow is equals to c. So the limit b sub 2 minus raised to k, negative k rather, plus 1 minus b sub 1 raised to negative k plus 1 over negative k plus 1. Okay? So, substituting now the value of the constants where c is equals to pb raised to k. Okay? So, for this here, we have p sub 2, b sub 2 raised to k multiplied by b sub 2 rather, minus raised to negative k plus 1 minus b sub 1, b sub 1 raised to k multiplied by b sub 1 raised to negative k plus 1 over negative k plus 1. So, again, multiplying b sub 2 raised to k plus, multiplied by b sub 2 raised to negative k plus 1. So, that result is b sub 2 raised to 1. So, we do not write the exponent 1. So, therefore, the work non-flow now is equals to p sub 2 b sub 2 minus p sub 1 b sub 1 over 1 minus k. Okay? So, or simply, PB is equals to MRT. We substitute also PB is equals to MR multiplied by the change in temperature over 1 minus K. Okay? So, I think class, it is very clear to everybody. Okay? So, another for heat transferred. So, if we again look at the TS diagram, so knowing from the condition that the heat transferred is equal to the area under the TS diagram, but for S is equals to constant, therefore D is equals to 0. That is why Q is equals to 0. Okay? So, next is for the change in internal energy. Whether you like it or not, as what I have said, delta U is always equals to MCV delta T. And again, for the change in enthalpy, delta H is equals to, again, MCP delta T. Okay? For the change in entropy. Okay. So, again, delta S equals to the integral of dq over T, and since delta S is equals to 0, therefore, from the TS diagram, delta S is also 0 here. Okay? So, and also, for the dq, since heat transfer is also 0, so therefore, delta S is equals to 0. And the last one is for the steady flow work. So, we know already that the work steady flow is equals to the area behind the PB diagram. Okay? So, where that work steady flow is equals to the negative integral of B differential pressure. Course limit from 1 to 2. Oh, again, PB raised to K is equals to constant for isentropic process. And then, getting now B, that is C raised to 1 over K, and then over P raised to 1 over K also. And then, so substituting now the value for B. So that is equals to the integral, negative integral of C raised to 1 over K, and then P raised to negative 1 over K, because this P is located at the numerator, and we bring it up to the numerator rather. Okay? So, multiplied by the differential pressure. Okay? So, again, putting the constant outside the integral sign, and then that is now equals to negative c raised to 1 over k, integral of p raised to negative 1 over k, differential pressure. Okay, so applying now the limits. So p sub 1 to p sub 2, therefore the value now of the work steady flow is equals to negative k multiplied by p sub 2 b sub 2 minus p sub 1 b sub 1 over k minus 1. Okay? But this term here is equals to the work non-flow. Okay? So work non-flow. Therefore, we just multiply the work or the non-flow work by the constant k. So we now get automatically the work is the flow of the process. Okay? So I think it is clear. Okay? So let us now consider the example here. Okay? So 1 pound of gas undergoes an isentropic process from 95.3 psi gauge and the volume of 0.6 cubic feet to a final volume of 3.6 cubic feet. Okay? So if Cp is equals to 0.124 and Cv equals 0.093 BTU per pound degree Rankine, what are A, T sub 2, B, P sub 2, C, delta H, and D is the work steady flow. Work non-flow rather. Okay, so solution from the ideal gas equation, PB is equals to MRT and then getting the value of T sub 1. So substituting all the given values, T sub 1 is equals to 394 degree Rankine. Okay? So, next. So, from the equation, from the derived equation T sub 2 over T sub 1 equals to P sub 2 over P sub 1 raised to K minus 1 over K, or that is equals to B sub 1 over B sub 2 raised to K minus 1. Substituting values of the volume, T sub 2 is equals to 218 degree Rankine or negative 241.8 degree Fahrenheit. Okay? So, getting now the change in enthalpy. Okay? So, again, change in enthalpy is always mCv delta T. Substituting all the values, the delta H now equals to negative 21.96 BTU. Okay? So, for the work non-flow, so again, from the derived equation, that is P sub 2, B sub 2 minus P sub 1, B sub 1 over 1 minus K. Again, substituting all the values, work non-flow now equals to 15.6 BTU. Okay? Thank you very much, class. Okay? So, that's all about my presentation. Thank you.